Hey everyone, and welcome to my last video on Numerical's ODE solver. In this video, we'll be talking about using Matlab's events functions to stop Matlab's ODE solver early. So far, we've only talked about three basic inputs. There's ODE fun, or what I usually call s dot, which is our derivative of our state vector, expresses some general function of time in our state variables. We've talked about the time span, and we've talked about the initial conditions. What we haven't talked about is an additional input called options. And as you could guess, the options input is an input that you use to specify certain options for Matlab's numerical ODE solver. The cool thing about options is that it gives you a lot of liberty on how you can adjust Matlab's ODE solver. You can specify tolerances, you can specify events functions, you can specify other things. Now, we won't be actually going into a lot of detail with options. We'll only be talking about events functions, and we'll only be talking about events functions in some slight detail, and just enough detail that you'll need for doing some basic things. If you want to look into more details that Matlab's ODE solver has to offer with options, you can look that up online. And also, while we're going along, if you want more detail on Matlab's events functions, again, you can look into that stuff online. In general, when you're using options with Matlab's ODE solver, you'll be specifying them with a function called ODE set. So you'll write something like options equals ODE set, and then you'll specify in these parentheses here whatever you want to specify for the options. And then you'll put options into Matlab's ODE45, or whatever ODE solver that you're using. In our case, we're interested in specifying events, so that's what we're going to do. We'll use apostrophes, and we will have events, and this tells MATLAB that the next input will be our events function, and then we specify the events function. Alright, and similar to ODE fun, E function will be a function of time and our state variables. I'll call it sum h of t and s, because it's not going to be the same as this function over here. However, unlike ODE fun, this function is going to return three outputs, and none of them are going to be the derivative of our state vector. These outputs are going to be check, is terminal, and direction. Now, as far as I'm concerned, I'm sure that, and more importantly, as far as MATLAB is concerned, I'm sure that MATLAB doesn't really care what you name these guys, but when you're writing a program, you'll really want to make sure that these variables are names that make sense to you when you revisit the program, or if someone else happens to look at your program. For that case, it really isn't necessary to change the name of direction or is terminal. You might occasionally change the name of this variable that I've called check, but that's probably the only variable that it would make sense to change the name of. We won't really be talking about direction much here. It's something that allows you to specify further detail, I'll say, on events that occur. For now, we're going to leave direction as an empty matrix. Again, if you want more detail on how you can use direction, you can look that up in MATLAB's documentation. Leaving it as an empty matrix uses the default settings for direction. The next variable is terminal, is a variable that you will set equal to 1 or equal to 0. If isTerminal is set equal to 1, then MATLAB's ODE solver will stop once your event has occurred. If isTerminal is set equal to 0, then MATLAB's ODE solver will not stop once the specified event has occurred. So I hope that actually makes sense. It's kind of right there in the name. Is terminal do terminate? If is terminal equals 1, which is the same as saying true, then MATLAB will stop the ODE solver once an event has occurred. If is terminal is 0, which is the same as false, then MATLAB will not terminate the ODE solver if the specified event has occurred. You're probably wondering what in the world an event is and what determines whether or not an event has occurred. And that's determined by this last variable over here called check. Check is an interesting variable. If check equals 0, then that means that an event has occurred, as far as MATLAB is concerned. If check is not equal to 0, then an event has not occurred. And that's really all there is to the events function. Now that might sound kind of strange and vague because you don't really see a whole lot of numbers or equations here, just some simple representations. And what's the significance of check being able to equal 0 for an event to occur? We'll go over an example to explain all of that. But basically, you'll want to manipulate the value of check so that check equals 0 when you want MATLAB to stop its ODE solver. And we'll go over an example to make that a bit clearer. We'll keep the example really simple. We'll keep the example super simple. Let's say we have a cannonball. I don't really draw that well, so sorry if it looks silly. But let's say we have a cannonball that's being, shot into the sky, and let's say that it's being shot at an angle of 60 degrees, and let's say that it has an initial velocity of 50 meters per second in this direction. And for this example, we're going to neglect drag, which makes our lives kind of easier and really makes the problem super simple. And let's say that we're interested in finding out how long it takes for the ball to travel 500 meters along the x direction. So we want to know when x equals 500 meters. Now obviously you could solve this very easily by hand. This is a simple physics trajectory problem, but I'm just doing this so that we have a way to use MATLAB's events function very easily. Okay, now for this instance, we want our event to occur when x equals 500 meters. That means we want check to equal 0 when x is equal to 500 meters. A clever way to ensure that this occurs is to write this. We can say check equals x not equal to 500. And what this will do is, as long as x does not equal 500, this value will be true, and therefore will be a logical 1. Therefore, check will equal 1, and an event has not occurred. However, once x equals 500 meters, this statement will be false. We'll get a logical 0, and check will equal 0. Therefore, an event will occur. This is a very clever way to ensure that we can make an event occur, and we can make MATLAB's ODE solver stop when we want it to. Another way to do this, if you're worried about certain tolerances, is to say check equals x less than 500. In this case, once x is greater than or equal to 500, MATLAB will stop the numerical ODE solver. You'd really only have to do this if you're worried about MATLAB jumping a little bit past 500 when it's solving for x, and not considering this statement to be false once that occurs, which would then mean that MATLAB would continue integrating until the final time that you specified, and you wouldn't get the stopping point at when x equals 500. Now really you could actually probably fix this by dealing with the tolerance settings with MATLAB's ODE solver, but if you aren't really worried about that, or you want to tackle it this way, that's fine too. Now before we can actually do anything, we really need to know the state variables for our system, so we can have something to actually integrate in MATLAB. So we can do the sum of the forces in the x and y directions. And in the x direction, it's really simple. There aren't any drag forces, so the sum of the forces in the x direction are 0. And that equals the mass times the acceleration, and that means that the acceleration in the x direction specifically, well, let me get rid of this equal sign. That means that the acceleration in the x direction is 0, which means that x double dot is 0. Really easy. You did not have to express this guy in terms of our lower order terms. In the y direction, we can sum our forces also, and that will just be the weight, obviously. mass times the gravitational acceleration. This will be negative because the gravity is pulling the ball down, and I'm going to assume that positive direction for the y direction is upwards. So this is a negative mg. With that being the case, that equals may, and that tells us that the acceleration in the y direction is equal to negative g, which means y double dot equals negative g. Again, this is a very, very easy problem, so we got the expression for our highest order derivatives very easily. If I'm interested in knowing the position and velocities over time, then I'll have 4 state variables. So my state vector will be S1, S2, S3, and S4. And that will just be x, x dot, y, and y dot. If I want the derivative of my state vector, then that will clearly be x dot, x double dot, y dot, and y double dot. And thankfully these are super easy to get due to this laughably easy problem. X dot is just S2, x double dot is 0, y dot is just S4, and y double dot is simply negative g. So now we have the derivative of our state vector expressed as some general function of time and the lower order terms, or more specifically our state variables, to keep things in accurate terms. And I want to point out something very briefly before we hop over to Matlab. Okay, this is what we want to specify, right? We want check to equal 0 when x equals 500, right? But recall that our events function is going to be some function of time in our state variables. So instead of using x, we're going to be using S1. And I'm writing that in both places depending on, which one you decide to use. But we're going to use this, S1, because we need our state variables, all right? That's pretty much all we need. Now we can go ahead and leap over into Matlab and look at what our events function can do. So we're in the Matlab environment for the last time, or at least the final time in this series on Matlab's ODE solver. And again, we're going to be doing things a bit differently this time. You can see that I don't have 3 separate files up as usual. I'll actually only really be showing you guys the function method. Technically, you'll also see the mfile method, but you won't see a function handle method, and the reason for that is I couldn't really find a way to use events using the function handle method. I imagine a way might exist. I did some research online, but only very briefly, about getting function handles to return multiple outputs, but if I recall, there are some complications in that. But this just goes to show the limitations, again, of the function handle method, right? I wrote all the code out. Here's all the code, although it doesn't work, so you don't really need it. And the only real problem is here. As I explained in the matrix video with, part 2C of this series, function handles are designed to return a single output. It can be designed to return a single scalar, a single vector, a single matrix, and of course, if you make a function that returns a scalar, and then you input a vector, then you're going to get a vector out as long as you set up the function correctly. But that's just by nature of what input you used, and that vector wouldn't be a single input exactly. It would technically be multiple inputs as far as the function sees, and so the function will return multiple outputs. Outside of those cases, which, adjust things in obvious ways, function handles are designed to return a single output. Again, vector, matrix, scalar, whatever. And our events function that we talked about earlier, the events function needs to be a function that returns 3 outputs. Now, I tried to get around this by making a vector, right? So I made a vector, and if you don't understand this code, we'll go through it over here when I write it. Haven't written it yet. But I tried to do this and be clever. I thought, okay, if I make a vector of values and make that get returned by our happy little um, function handle, that it'll work, right? And the declarations work up to this line. So if I were to run this code, you'd see that it's awaiting a response. So at least no obvious errors from MATLAB yet. But then if I try to run the function the normal way, we get an error. And the error says insufficient number of outputs from right-hand side of equal sign to satisfy argument, or satisfy assignment. Right, so I'm sure this has to do with an issue with using a function handle and the fact that function handles are designed to return a single output. MATLAB might see this as this entire vector not being a, how do I want to say this? Not being a, three different things like check, is, terminal, and direction, but instead being vector values for only check. And if it's doing that, then obviously it's not getting all the outputs that it needs, and so it returns an error to me. So this is again one of those situations where if you're trying to do the function handle method, you might be limited here. It might work. There might be a way that I'm unaware of or that I just missed in the midst of this programming, but it'll require more work and more jumping through hoops. So here we really want to resort to the function method. And so let's go ahead and go through that. I set up the basic things for what we would need if we were just going to integrate it the normal way. I have the initial conditions and I've separated the velocity into the appropriate components. Here's x, the initial x position, the initial x velocity, the initial y position, the initial y velocity, my initial conditions vector. Here's my times, right? And we're looking at going from 0 to 30 seconds. I call the numerical integration. And you see that I have options here. We haven't declared options yet, but I have it here for when we write it out. And then I'm going to plot the trajectory as well as the x position over time, because I want to see that we did indeed stop when we got to 500 meters. And then here's the function that returns s dot. This is a very simple function. I only use 2 lines. Just quickly declared g and then declared the derivative of the state vector. Didn't even need to take up multiple lines. No need to take up multiple lines at all. Very simple. So now we need to write our events function so that we can get MATLAB to stop this solver early, and specifically stop it when x equals 500 meters. So let's make a function. It needs to return check, is, terminal, and direction. And I'm going to call the function events. And remember, this function is a function of time and our state variables. Like I said, we're going to keep direction as an empty matrix. Is, terminal is going to be set equal to 1. And I'll comment this code out too. This just means use default settings for direction. And for here, we want to terminate integration when event occurs. And finally, check is going to be x less than 500. This is what I'm going to use. Obviously, you could use, the squiggly and equal sign if you wanted to, but I'm going to use this. Now, recall what I said. We can't use x. It's not going to know what x is. We're looking at our state variables, and x corresponds to s1. So I'm actually going to use this. And this is going to tell me that an event occurs when x is greater than or equal to 500 meters. Because check will equal 0 when x is greater than or equal to 500 meters. And when check equals 0, an event is said to have occurred. Now I need to do one last thing. I need to change this to a double, because this statement here is naturally a logical value, right? It will be a logical 0 or 1, but we want it to be a regular number that MATLAB can operate with. We're going to treat this as a double, or we're going to convert this value to a double. Here's the function. It's as simple as that. End this function. And then up here, we want to call ODE set to get our options. So options equals ODE set. Remember, we have events with a capital E in those apostrophes, and then our function, which in this case is just events with a lowercase e. So at events, and put a semicolon here, and that should be it. This function is called trajectory, calling that guy here. If we run this function, it should work okay. And here are the results. So looking at this plot, we see that we have the trajectory, the x displacement, the y displacement, and over here we have the displacement, the x displacement specifically over time. And as we can see, it looks like this guy stops at 500 meters. We could request MATLAB to show us the final value of x after the integration. So if I say x and, it will show me. And as we can see here, the final value for x is indeed 500 meters. So going back to this plot, this also makes sense. If the initial x position is, or sorry, not position, if the initial x velocity is 25 meters per second, again, the x velocity, not the total velocity, right? If the initial x velocity is 25 meters per second, then in 20 seconds, it should reach 500 meters. So we could have calculated that stuff by hand. We're just, saying that MATLAB can get the right result also. And here's the trajectory if we want to see that as well. That's pretty much all there is to it. Now, what about the mfile method? For the mfile method, we have these two separate functions, so I'll actually have to make two separate mfiles. I could copy this function and paste it here. And I would probably rename this guy, but I could paste that guy here, and then copy this function, which is our events function, and paste it in this m file, and then save both of these guys, right? And then, whether in the command window or in a separate m file, I would have to call ODE set first to give me options from our events function, and then after I do that, I would then have to call ODE45 using our regular function that returns s dot. Now this is the reason why I don't like using the mfile method, because you start having to make multiple mfiles that really just relate to one specific problem that you're working with, unless you're leaving it really open-ended to handle multiple kinds of problems. So in this case, I like the function method because I can keep everything clearly in one area and debug it all in one area. But you can always choose whatever method you prefer. I'll close these guys out. And that's pretty much all there is to it. You can get really creative with check, or the value that you use to check if an event occurs to handle your problems. And I actually want to show something with that. Let's say that instead we wanted to see, we wanted to integrate only until we got to the maximum possible point for y, right? The highest point. Okay, that's possible too. And we can do that not by looking at the y position. We could use the y position, but that would require us calculating the maximum y position by hand and then doing logical stuff. We don't want to do all that work. What we can do is use the y velocity, because what we know is when the y velocity becomes 0, the y position is at a maximum or minimum. Obviously, for this particular physical scenario, there will only be one critical point that will be a maximum for y, and that's what we want to look for. So instead of having this, what I can do is look at the velocity, and the y velocity is s4. And that's all that I need, because s4, the velocity in the y direction, will naturally start positive, naturally go to 0 when the y position is maximum, and then naturally go into a negative value and get more and more and more and more and more negative, right? So when this guy equals 0, when the y velocity is 0, is when we get our maximum y position. So we can just use this for check. And if I run this, you'll see that we stop at the maximum y position. So this does work. It's really cool. That's just another thing that you can do. And again, as you deal with other problems and you want to stop your integration at particular points, you can get more creative with how you adjust this value for check. But just remember that you want it to be 0 when you want an event to have occurred. And a question that many are probably wondering is, can you have multiple events that you're checking at the same time and these different conditions that you're working with? And the answer is yes. I don't want to leap into the details of how to deal with, checking multiple events at the same time and seeing how that affects is terminal and direction. It will involve vectors, but that's more detail than I'm going to go into. For that, again, you can look at MATLAB's documentation, but that concludes this video. So that's actually our whole series with MATLAB tutorials. I hope that it was helpful in getting you more familiar with MATLAB's ODE45 solver. A lot of people that I know really don't like using MATLAB for the numerical integration, especially for their school problems, but it can be really powerful and give you a lot of freedom if you know how to use it. So hopefully this video was helpful, and hopefully you can go on to do more and more cool things with this solver. And as always, good luck in your MATLAB ventures. Thanks for watching.